Hello students. Today I'm going to go over inferential statistics with you using SPSS. And just like I did with descriptive stats in the last little video, um, I'm just going to sort of walk you through the process using SPSS. Remember this, the decision tree? We already talked about descriptive stats, so now let's go into exploring relationships between variables, and we'll go to the first one, the chi-square goodness of fit test. Let's say that you have some data, and there are men and women among your subjects, and you want to know, did you get a representative amount of men and women in your experiment? What you would do is you would go to your data. This should look familiar to you guys. This is the data that we've explored previously. You would go to, let's see here, analyze, non-parametric tests. Non-parametric means that the assumptions for a parametric test have not been met. Those assumptions are things like normal distribution, interval ratio data, and there are some others. But so in the non-parametric side, you go to one sample, and I already set this up, but I just want to sort of show you how you go through it. Instead of automatically comparing observed data to hypothesized, we would customize the analysis. And when it comes to fields, the test fields, it just automatically puts everything in there. I actually, here, hold on, I'll show you how it looks to begin with. It looks like this, okay? That you don't want. Then you're going to get a one sample test for all of these people, all of these variables. So you just hold shift and the down button, get rid of the ones you don't want. And what we really are interested in is the gender evenly distributed. Then go to settings, and this is the default that it automatically chooses the test based on the data. But I like to just ask it directly to do a chi-square test. And you can either say that all categories have equal probability, which would be true for men and women, right? It's 50-50 in the population. Or you can customize expected probabilities. Let's say that you want to know if you have a representative sampling of race based on the American society as a whole. So then you would know, you would have to find out from census data what percentage of the population is African American, Latino, Asian, white, and so on. And then you would put that information in here, and you would compare what you have to the frequency that would be expected to see if you have a representative sample. Here I just check all categories have equal probability because men versus women are equally probable. Then just click on OK and run. And what we have here is reject the null hypothesis. Well, what does this mean? What this means is that we do not have an even distribution of men versus women in our group. And that means we have more of one gender. So let's take a look at that. Descriptives, frequencies, gender, okay. And then what you can see is we have 18 women and 7 men. So that should fit, right, you guys? That is not, ordinarily we'd see 12 and 13 or something like that. That would be 50-50. And it becomes increasingly unlikely that it's a random sampling of the population, the more different these counts are. And our decision to reject the null hypothesis just means that we do not have an even distribution of men versus women. Okay, so that's the chi-square goodness of fit test. Then there's a chi-square test for association. This is when you would have two variables, and let's just look at our data again and choose something. Well, let's choose this one. We have openness to experience. You're either curious or you're cautious, versus this one, extroversion. You're either outgoing or solitary. And what we want to do is we want to find out if there's a relationship between those two. So to do that, we go to non-parametric. We look at one sample. No, we wouldn't. Sorry, hold on a second. Analyze. Non-parametric. One sample, yeah, it would be. And the fields would be, take this one off, and add openness to experience and extroversion, and go to settings. And we'll just stay there with the chi-square test and hit run. Okay, now what we have is not what I wanted. Okay, this is a one sample chi-square test for openness to experience, which that looks like that's evenly distributed. And the other is extroversion, and that looks like it's not evenly distributed. Let's just take a look at that. Okay, descriptives, frequencies, openness to experience, extroversion. Okay, so yeah. Okay, now this makes sense, right? See how this is not significant? That's because we have 13 people who are curious and 12 who are cautious, evenly distributed, right? And over here we have 20 who are outgoing and 5 who are solitary. So that would be not evenly distributed. But what I didn't get it to do, is what I wanted it to do was to tell me if there's a relationship between those two. And I think I just found it strangely under, okay, here, check this out. So you go to descriptives and you go to crosstabs, okay? And then for row, we'll say openness to experience. And for columns, we'll say extroversion. And then look at statistics and click on chi-square and then hit continue and then hit OK. Now what we have is the crosstabs. Okay, you have on the open to experience line, among curious people, 12 of them were outgoing and 1 was solitary. Among cautious people, 8 were outgoing and 4 were solitary. And so our question is there a correlation between a relationship between openness to experience and extroversion? And I think we would probably expect that there would be a relationship there, even though, and this is a side note, these 5 factors are supposedly orthogonal, which means they don't really interact that much with each other. But if we look at the significance, what we'll see is that the significance is not below 0.05. That's the magic number that we're looking for here. So under Pearson chi-square, the significance is 0.109, meaning that we do not reject the null hypothesis, meaning that we would say there is no significant relationship between openness to experience and extroversion. Now, having said that, 0.109 is not that far off from 0.05. And so it looks like there might be a little bit of a trend there. And it kind of does make sense that people who are curious tend to be more outgoing, and people who are cautious tend to be more solitary, right? So you guys see how that relationship looks like it's starting to take place? That's what if we had a bigger sample and more people in it, we might find actually there is a relationship there. I'd be surprised if there wasn't. Okay, now I hope I didn't confuse you too much. I'm going to do one more just so that everyone feels comfortable, that they understand what I'm up to. So let's just do agreeableness and conscientiousness, okay? So we go to analyze. We go to descriptives, even though we're not really doing a description, we're doing an analysis, but oh well. And we go to crosstabs, take these things out, and I forgot what I said we would do. I think we're going to do agreeableness with conscientiousness. And statistics, chi-square is already up there. And cells, no, continue. And cells, okay, no need to change the defaults on that. And then just click on OK. And what do we have? So we have organized and careless, and friendly and cold. Now if you look at the significance here, this is even less of a relationship right here at 0.238 than what we saw on the last one at 0.109. So whereas this one, we kind of felt like, or at least I felt like there was a trend there between extroversion and openness to experience being related to each other. When it comes to agreeableness and conscientiousness, they really don't seem that closely related. Now, having said that, notice that we only have 3 people in the cold category. So when you really don't have that many people, it's hard to be too confident that your results are meaningful. Ideally, you'd have enough people in each cell that you could see a relationship if one exists. But in any case, what we have here is 15 friendly people are considered organized and 7 are considered careless, whereas 1 cold person is organized and 2 are careless. So, I mean, you could say, well, half of the people, it's half of the people who are friendly are careless, but twice of the people who are cold are careless. So maybe, again, with the bigger sample, you see a relationship that we don't see with this small sample. Okay, I hope that helps, though, and I hope that has helped you guys to understand how to run chi-square goodness of fit tests and chi-square tests for association. The next one that I want to try is the Spearman's row, which is just the Spearman correlation. And we'll go to our survey again. And now what we're looking for is variables that are ordinal to see if they correlate with each other. For this one, I'm going to correlate attractiveness with happiness. These are all, remember, on a 1 to 10 scale. So I go to Analyze, and I go to correlate, and I go to bivariate, which just means two variables. And what did I say? Attractiveness and happiness. What do you guys hypothesize? I imagine you're thinking there's probably a significant correlation there, but we'll see. Okay, I don't know if you guys noticed me doing this. I just want to be very clear that I chose Spearman because it is a two variables that are both measured ordinally, and that led me to Spearman. So that's why when I was setting up my box here, I unclicked Pearson, which is the default, and I clicked Spearman. Okay, and then I click OK, and let's see what we get. Here we have the relationship between attractiveness and happiness is the significance is 0.188. And again, we're looking for 0.05 or less there. 0.05 or less would tell us that there's a significant correlation. Anything over 0.05 tells us that there is no significant correlation. And so what we can say is, at least in our sample, there's no significant correlation between how attractive you are and how happy you are. And so those of us who are less attractive can rejoice that we can still be happy. Okay, so that's a Pearson correlation, a Spearman. And now let's go to Pearson. Pearson would be to correlate two variables that are interval. In our data, we have under scale, we have years of education, yearly salary, number of marriages, estimate of IQ score, weekly hours worked, weight of subject, and height of subject. Let's try for this first one, salary and years of education, okay? So years of education is right there. Okay, so we'll go analyze, correlate, bivariate, take these two out, and we said years of education and yearly salary. Unclick Spearman and click Pearson. Why are we clicking Pearson? Because we have interval ratio data that we're correlating. And then click OK. And now what you have is, oh, it's so very close, isn't it? The significance is 0.056. Now, it's not significant, but it's pretty close. And this is a good example of when you would feel pretty confident that with a big enough sample, you would find a significant correlation. I think people always feel a little confused, by the way, about these boxes, and they just wonder what's going on. Let me show you that. Here, years of education is being correlated with years of education. It's a perfect correlation, right? Well, that shouldn't surprise anyone. Whenever you correlate anything with itself, you'll get 100% correlation. But over here, this is correlated years of education with yearly salary. The Pearson correlation is 0.387. So the way you'd write that is little r equals 0.387, and then p equals 0.056. Or you could say p is greater than 0.05. And this is just the mirror image of the above one. Here you have the exact same numbers because it's describing the same relationship. Okay, so that's how you do a Pearson correlation. Now back to our testing, our statistics decision tree. Now we're looking at significant differences. And I'm just going to take us right to the independent samples, no, the one sample t-test, okay? And what I'll do is I'll show you guys that, oh, hold on, that's output. Okay. Let's take IQ. You can see here in our data view that, let's see, where is our IQ estimate? Oh, here it is. Looks like it's going to be significantly greater than the average. Remember that the norm in the population is an IQ of 100 with a standard deviation of 15. So let's take a look at that. Analyze, compare means, one sample t-test. Our test variable is intelligence. Where are we? And oops. Test value should be 100. Okay. So our mean is 116, and what you can see here is that the significance is 0.000. In other words, there's a significant difference between our sample, which has a mean of 116, and the normative group, which has a standard, a mean of 100. Okay? And now let's just move right along to a independent samples t-test. You might be wondering, why am I skipping Mann-Whitney U-test? And it's just in the interest of time. I found that people they're much more likely to do independent samples t-tests than a Mann-Whitney U-test. So if you need to do a Mann-Whitney U-test, you'll be able to sort it out. But I don't want this lecture to get too unwieldy. So now we're going to do an independent samples t-test. And what I'd like to try is just gender by IQ. So we'll do analyze, compare means, independent samples t-tests. Gender subject will be the grouping variable. You have to define the groups here. And for gender, we had 1 and 2. So this might sound silly, but you just do this. You put in a 1 on group 1 and a 2 on group 2, and you say continue. And then the test variable will be estimate of waste. Options, no options necessary, and OK. And now what we have is a t-test. Now, for females, we had 18 of them, and we had 7 males. The mean IQ for women, 116. The mean IQ for men, 115. But you know, if you round it, it's actually exactly the same, 116 for both of them. So just looking at these means, I think we can feel pretty confident that the t-test will not be significant. I think people sometimes get confused when they look at this box right here. So I want to walk you through it. The first thing that the independent samples t-test tells you about is equality of variances. And there's something called Levene's test. And just so you know, the first thing it'll do is it'll ask the question, is there a significant inequality of variance? If this is significant, then you should look at this line, equal variances not assumed, when you're trying to figure out if there's a significant difference. If this number is above 0.05, which in this case it is, then you can look at this line, equal variances assumed. Now, as you can see, it's not a huge difference, but the number that you'll report is t equals 0.114, significance or p-value equals 0.910, or P is greater than 0.05. In this case, much greater than 0.05. There's really no noticeable difference in IQ between men and women in our sample. Okay? Now, we're going to go right over to one-way ANOVA. And here, I will show you a little trick that I did. Remember how we have this question on education, which is actually interval ratio. It ranges between 0 and 21, but I recoded that into edu category. And edu category was one of three choices: high school, college, or graduate school level of education. So by putting it into three categories, I can now look at it in an ANOVA situation. And so watch how I do that. To compare means, I do a one-way ANOVA. Now it's called one-way because we're just using edu category as our factor, and then dependent is going to use salary. Okay, and then we'll hit OK. And what we have here is, it's not significant, but it's close again. So the way you would report this is that in our sample, there was no significant difference between people who went to high school, college, or graduate school in terms of their yearly salary. F equals 2.79, P equals 0.083, or you could say P is greater than 0.05. Now, that is our one-way ANOVA, and now I'm going to go to a multifactorial ANOVA, which just means that you have more than one independent variable. So go here, go to variable view, and now I'm going to include not just education category, but I'm also going to use gender as a independent variable, and I'm going to keep income as our dependent variable. So now, watch this. I go to where do I go? Mixed models. No. I go to general linear model, univariate. I'm just going to hover here for a second and just make sure that you guys are with me. We're going to a multifactorial ANOVA, and the way to get there is general linear model, univariate. Univariate because we only have one dependent variable. Now our dependent variable again is going to be salary, yearly salary, and then our fixed factors, or our independent variables, are going to be gender and education category. And let's see here. For post hoc tests, just look at the means in each category. to see if they're significantly different. There are a lot of possible post hoc tests that you could use. Let's just use LSD, which stands for least significant difference. Okay, and then we'll hit OK. Now what we have here is, first of all, please don't get overwhelmed. We have a bunch of F values. The first thing to do, though, is to just ignore these up here and go to gender. And here you can see that there's no significant difference between genders when it comes to salary. 0.252 is bigger than 0.05, obviously. And so the F value is 1.397. That would be what we call a main effect. A main effect is there a difference between the different levels of one particular independent variable on the dependent variable? So on the independent variable of gender, the dependent variable of salary, there's no significant difference. For education category, this shouldn't surprise you. No significant main effect. Does this number 0.067 look familiar? It should, because when we did the ANOVA, oh, it's 0.083. Anyway, it's close. The reason it's not exactly the same is a sort of technical, don't worry about it. Okay, and then finally over here is something called the interaction. It's not significant. The last part of this is post hoc tests. If you can think of the ANOVA as asking the question, is there a significant difference between, let's say, education categories and all and salary when it comes to all categories? The post hoc test asks the question, well, is there a significant difference between college and graduate school, high school and graduate school, or high school and college? So if we look at that, we can say that the difference between high school and college is not significant. But the difference between high school and graduate school is also not significant, but it's kind of almost there, right? 0.055. So remember, we're looking for 0.05 or lower. Now this kind of makes sense, right? People who finish graduate school really should be earning more than people who don't even go to college, and that's sort of playing out there, but not in a significant way, but close to significance. And here we have college versus high school, not significant, and notice it's the same number as there. And here we have college versus graduate school, again, not significant. But what you can sort of starts to emerge here is that it seems that people from graduate school really are, closer to being significantly different in pay than people who go to high school and college. They tend to be closer together. Okay, so that is what I wanted to accomplish today. I apologize if that felt overwhelming. And of course, the beauty of this is you can watch this a few times. When you're ready, you can take the quiz, which will be online, and it's just going to ask that you choose the appropriate statistical technique and run it on SPSS using this data that is available on the Canvas course, classsurvey.save, and then you'll be done. As always, if you have any questions or you want me to go through this on a more individual one-on-one basis, I'm happy to do that. And I wish you happy studying.